Right, good morning everyone, and welcome to the second lecture of linear free energy relationships. For this, I'm not going to be placing tasks on Are You Connected? There are tutorials available, and if you would prefer me to mark them rather than marking from the solutions that are available, you're welcome to email me and I will send you back a mark for that with suggestions for improvement. So, just a couple of things I want to remind you is that we're working a lot with benzoic acid. And of course, I'm going to use the marker structures for benzoic acid. But as we've seen in the past lecture, we're not going to look at the orthoderivatives because the orthoderivatives have a steric cost in some reactions. So we will work with aromatic systems. They must have aromatic substituents near a reaction center, but we'll look at aromatic systems that are substituted at the meta and para positions. Just have a note that over here, when I draw a nitric group, I hope you're familiar with drawing the nitric group with a plus on the nitrogen and one of the oxygens with a negative charge. Okay, so we ended the lecture, well, we were having a look at two reactions. We're looking at the acid dissociation of benzoic acids, and then we decided that aliphatic ones are not so great, so we removed them, and we decided that the ortho-substituted ones aren't so great. So we went down to meta and para-substituted systems. We're comparing the acid dissociation against the base catalyzed hydrolysis of esters. So just to remind you of the base catalyzed hydrolysis of esters, what we have is our aromatic group now. We're only going to work with aromatic systems, okay, substituted at the meta and para positions. And what happens is that when this tetrahedral intermediate gets formed, the meta and para substitute positions do not interfere with what's going on at the reaction center. Okay, and of course, by doing so, we find by removing the ortho substituents and the aliphatic substituents, we end up with a beautiful straight line. Of course, I'm only showing the esters here. These are the esters that get hydrolyzed, so I'm only showing what's happening on that, but you can figure out the corresponding benzoic acids. So on this axis, we'd be looking at the paramethyl benzoic acid. Over here on this axis, this is just H, so it's just the unsubstituted benzoic acid, and on this for this point would be the paranitrobenzoic acid. Okay, and then of course, if you extend it to other derivatives, you still get the straight line, and I hope you notice that there's a lot of scatter along the line, and that's expected, and that's not due to error in experiment. That's because we are comparing two slightly different things. So we are comparing the free energy of change for this reaction against the free energy of activation for a totally different reaction. So the question I have now is, what is the point of comparing these totally unrelated reactions? Well, they're not totally unrelated. You've got the aromatic system with the associated substitution on that. So what is the point of comparing them? Well, if you look very carefully, of course, with the substituted benzoic acids, so for instance, paramethoxy benzoic acid or paramethyl benzoic acid or parachlorobenzoic acid, we know the pKa's for all of these. Although I'm not going to work with pKa's in this, I'll rather work with log Ka's. We can see that at one end of a spectrum, at one end, those with the higher pKa's, they've got a higher pKa because they've got electron donating groups like methyl and methoxy groups, paramethoxy groups on the aromatic system. And those with the lower pKa's have the lower pKa because they've got electron withdrawing groups on the aromatic substituent. What this means is that when you have a look at this graph here, if we have used this acid dissociation of the substituted benzoic acids as our reference, we can say that on the left-hand side of the graph shows what happens with electron donating groups. The right-hand side shows what happens with electron withdrawing groups. And then we can use that as a basis for comparison when we look at the rates of hydrolysis. When we look at the rates of hydrolysis, then we can see that the rates are very high where electron withdrawing groups are concerned, and the rates are very low where electron donating groups are concerned. So don't forget what we're plotting. This here, the R is aromatic. It's meta and para-substituted aromatic. So that's important. So just see over here, I've drawn it with a slightly different, not the marker structure, but slightly differently here, just to remind that we're only working with meta and para-substituted systems. And don't forget that we're comparing base catalyzed hydrolysis with this acid dissociation, which tells us about electron donating groups and electron withdrawing groups. Okay, now there's a slight problem with this axis, and historically what's happened is that it would be really nice if we took the unsubstituted case. So the unsubstituted where the R is H. So this is just benzoic acid down here, and this is just ethyl benzoate hydrolysis over here. It would be nice to take that H, which is neither electron donating or electron withdrawing, and put that at the zero of our axis. So what I would like to do is to shift this entire graph down so that this hydrogen is at the center of the axis. And that is quite straightforward to do. If we want to make that the center of our axis, look at our x-axis to start off with. Our x-axis goes from minus 4.46. The unsubstituted is minus 4.19. And the for the electron withdrawing groups, it goes to minus 3.41. So see these numbers here. All we have to do is subtract minus 4.19 to all of these, and that will make that 0. So for the x, what we can do for that x is we just subtract minus 4.19, which is the same as adding 4.19, and you'll see that that comes to 0. And we'll do it to the others. So let's add 4.19 to that, and we get minus 0.17, and so on. And we'll then have a range of numbers that I'll call the substituent parameters that go from a negative value for strongly electron donating to a positive value for a strongly electron withdrawing group. Don't lose sight of what we're looking at. These numbers here come from the log Ks of the benzoic acids, the acid dissociation of those benzoic acids. That is our standard. Please don't forget that all the graphs from now will use that standard as the x-axis with not these numbers, minus 4.6 going to that, but they'll use numbers where 0 is right where the unsubstituted is, so that the electron donating groups have a negative value, and the electron withdrawing groups have a positive value on the axis. So we're going to change it. We're going to go from the log Kas, shift it so that hydrogen's in the middle, and now we have the Hammett substituent parameters that go from negative for electron donating to positive for electron withdrawing. Okay, so that is how we derive the Hammett equation. So for our x values, we subtract this negative value, making it a positive, so that comes to 0. But we will have to do the same for the y-axis. For the y-axis, you're also going to have to subtract this minus 1.2 here to all values, so that for the unsubstituted ester, we want that to be at 0 as well. So you have to do the same on the y-axis. But that we'll have to do for every individual reaction ourselves, and I'll show you how to do that. But what's nice about these Hammett substitution parameters is that people have studied this reaction so well that there are tables and tables. These values are readily available for all substituents that you could possibly think of. Aromatic substituted systems substituted at the meta and para positions. So if I wanted to derive the Hammett equation, this is how it works. So don't be put off by this. So firstly of all, we've just got to remember that we plotted the log of big K as our x and the log of little k as our y. And if you use y is equal to mx plus c, we've got y's are the logs of little k's. Your m, I'm going to give a special name called rho. And it is a very good reason for choosing rho, because rho sounds like r, it's a reaction. And so it's a reaction constant. So the gradient is rho, and your x's are the log k's. Plus, of course, you've got this horrible intercept that you have to get rid of. So what we do is we have a look at our x reference and we look at our y reference. Now, our x reference is the unsubstituted one. So what we need to do is we need to subtract this value from all the x's. And so here it is. We subtract the value for the unsubstituted case, which was, if I go up, it was we subtracting minus 4.19. We subtract minus 4.19. So all of that is minus 4.19. We're going to subtract it from the general equation. So this is a number, a single number. We can calculate it as a single number, or we can read it from the graph as a single number. We're going to subtract this from all the x's. And similarly, we're going to subtract the y value that we want as 0 from all the y's that we have. And so let's subtract the unsubstituted. See the h there says it's unsubstituted. These are an exact value, and these are all the rest of the values. And when you subtract it, you get log kx minus log kh. There we go. And that means that when you're at the unsubstituted case, you're going to be at 0. When this is kh, you'll be at 0. And of course, here's the x values, and the c's, when you subtract, the c's disappear nicely. And of course, you can see over here that when you are at the unsubstituted case, when you put kh here, this comes to 0. So your graph is going to go beautifully through the origin. And so the Hammett equation then is this. It's log kx minus log kh is rho times that. But of course, you can use the laws of logs to know that the log of k of x minus log k of h is simply the log of division. And of course, log kx minus log kh is simply the division. But these are the values. These values here are the ones we had in the previous slide, which we called sigma s, the substituent parameters. So we know that the substituent parameter for h is going to be 0. And then for electron withdrawing groups, we're going to have a positive. And for electron donating, we will have a negative value here. So what does this mean? It means that we can plot a graph. So if we want to study our own particular reaction, what we've got to do is we've got to have a whole series of rates of reaction for different substituents. Most importantly, you've got to have the rate for the unsubstituted system, so that you can go through your entire list and divide the rates of all the substituent reactions by the rate of the unsubstituted reaction. And once you've done that, and you've got that series of values, you can plot them against all these substituent parameters that we can read from tables. And once you've done that, you get the most important part of this, the reaction constant rho, which tells you in-depth details of what's going on in your reaction. Okay, but maybe it'll be clearer if we have a look at a specific example. But firstly, before I look at a specific example, don't be put off by this. So here, don't forget that we've got a reference reaction, which is over here. I might represent the benzoic acids using a marker structure, but you know that it means that we're going to, how do we get the sigma value? Okay, so just These are the sigma values. So that's a very good question. How do we get these sigma values? Let me go back. So you see over here, I'm going back to here. So here are the sigma values. You always have to look at your reference where your substituent is H. So it's aromatic with an H attached, which is simply benzoic acid. So your reference is benzoic acid, which has a log Ka of minus 4.19. We want to shift this whole set of values so that H is at the middle. So the way we can shift this is we just can simply add 4.19 to this. We add 4.19 to this, we get 0, and now we have our sigma value. And we add 4.19 to the others, and we get their sigma values. So this is how we get the sigma values. Does that make sense? Are you happy with how I get the sigma values? We've got to do some reactions. We've got to go into the lab and measure some Kas. Once we've measured the Kas, we can measure for a whole lot of different. So on the ring, we'll have paramethoxy and paramethyl. We'll have straight benzoic acid, parachlorobenzoic acid, paranitrobenzoic acid. Get all those benzoic acids, measure their Kas, subtract the log Ka of the unsubstituted benzoic acid from everything else, and you'll get this range of sigma values. Okay, so that minus 4.19 is really important because in here, that minus 4.19 fits in here. So we're subtracting the minus 4.19 over here at this point. So everything else is minus 4.19, and that's what's giving us our sigma values. But of course, in reality, maybe this will make it clear, we're going to look at tables. Now have a look at this table here, and let's think how to read it. First of all, let's have a look at H over here. If you have a look at H, it means that if we look at the structure, if you put H's around here, if you put an H at any position, it's unsubstituted benzoic acid. You're not substituting it at all. So it doesn't matter if you place it at the para position or the meta position, you're going to get 0. I had it as 4.19 in the previous slide. This is very close. You'll find that when you look in the literature, you look at tables, they sometimes differ in decimal places. So don't be put off by that. But the bottom line is that the sigma para and sigma meta are both 0 for the unsubstituted case. Okay. Now, of course, it's interesting to note that if you've got a methyl group, if you place it at the para position, your pKa is different to when you place it at the meta position. That means that when you get your sigma p for para position, it's slightly different to having a methyl group in the meta position. But of course, to do this, you've got to have meta-methyl benzoic acid and paramethyl benzoic acid. You've got to measure the Kas, and you've got to subtract the log Ka of hydrogen from it to get these sigma values. So these sigma values all come from many, many experiments in the literature. And so we don't have to go back and do those experiments at all. We just need to remember that all of these relate to benzoic acids, substituted benzoic acids, the acid dissociation to form H3O+. So you can check for anything. So for instance, if we're looking at parachlorobenzoic acid, so if we have chloro at the para position, it might be nice to know what its sigma value is, and we can simply read it off. And here we have sigma p, its sigma value is 0.22. So if we had any other reaction that had the aromatic parachloro substituted aromatic system connected to anything else, then we would be able to have a value on our x-axis that we could plot. This is the standard It is our reference reaction. It is the standard, and it's what we get these Hammett substituent parameters for. The sigma is not random. Sigma is chosen for substituent. And rho is for reaction, which we'll deal with later. So can I go back to our hydrolysis of esters? Here's our hydrolysis of esters. So I've changed it now. Can you see it's all shifted because instead of plotting log Ka's, I've plotted the sigma values. So it's all shifted by 4.19 so that the hydrogen is right at 0, the unsubstituted is right at 0, and on the left we've got, on the negative side, we've got our electron donating groups, and on the positive side we've got our electron withdrawing groups. So this is, and you'll notice that on this side, I haven't simply plotted the log of a rate. I've plotted the log of a rate minus log of a rate of the unsubstituted case. And so that's also shifted it to make sure that the graph goes through the origin. So this is interesting. So the point of this is that we're not interested so much in our reference reaction down on the x-axis. We're interested in the base catalyzed hydrolysis of esters. And it's interesting to note that in the base catalyzed hydrolysis of esters, we end up with a graph with a positive slope, and its slope is 2.55. That rho, the reaction constant for the base catalyzed hydrolysis of esters, is 2.55. Now, it might be worth examining why it has a positive slope. Look carefully at the graph. Note that if you put a paramethoxy group on here, a strongly electron donating group on this, it slows the reaction down. If you put a paranitro group on this, you can see that the reaction, the base catalyzed hydrolysis of esters, is really, really fast. What does it mean? Okay, there's a really interesting problem. What does it mean when sigma meta is positive and sigma para is negative? What does this mean about its electron donating, electron withdrawing effects? That is really a very interesting point. And so that's a fantastic point that's been mentioned. And I'd like you to just go back to the table and have a look at the methoxy group. You'll notice that when the methoxy group is in a para position, it's a strongly donating group. But when it's in the meta position, it is a withdrawing group. So that's really interesting. And we will, what does it mean about, and the same with the OH as well. So point also with the OH, the same thing is happening there. Maybe if I can ask you to be a little patient, because when we come to looking at pi systems, it might be more apparent as to what might be going on, particularly with these oxygen-containing groups. So what's happening is that there are two things in balance here. You've got the electronegativity of the oxygen, okay? But on the other hand, you have got lone pairs on the oxygen. So there's something happening about those positions that is causing these positions to be different. Okay, so they are expected. So be patient as we come a little later. It'll be beyond simple electronegativity. There'll be other factors that come in. Does that, is that all right for now?
Yeah, that's perfect.
Okay, perfect. Okay. Right, so question. We are looking at the hydrolysis of esters here. And so it'd be nice to explore why electron donating groups slow this down and why electron withdrawing groups make it go faster. And I have intentionally, on the next slide, looked at the meta substituents and not the para to try and avoid confusion where the sigma might go from positive to negative. Okay, so question is, what happens? What is the effect of electron donating, electron withdrawing? why does an electron withdrawing group make this go faster, and why does an electron donating group make the hydrolysis go slower? So if I want to explore an electron withdrawing group, I will always choose the nitro group. It's the strongest electron withdrawing group I can think of offhand. And of course, if I want to explore an electron donating group in the meta position, the strongest I can think of in the meta position is the methyl group. So I'm going to explore those too. So you will notice that if you place a nitro group, what happens is you've got the inductive effect, the electron withdrawing from the nitro group. And what happens is it pulls electron density away from the carbonyl, and it makes the carbonyl more slightly positive than it was originally. Can you see that this will then enable attack of that carbonyl by a hydroxyl group coming in? Is that apparent? Okay. And furthermore, it's not just that, but when the hydroxy group comes in, you form, I've neglected to draw the arrow that pushes the double bond onto the oxygen. You have this negative charge on the oxygen. And noticed that as that nitro group pulls electron density towards itself, it stabilizes that negative charge. So it's quite clear, simply looking at induction through the sigma system, through the sigma bonding system, it's clear to see why the nitro group accelerates the hydrolysis of the esters. So it's clear why there is a fast rate with a nitro group present. Now let's have a look at electron donating groups. So if you were to have a methyl group, of course, you'll notice that a methyl group pushes electrons, and it'll push electrons onto the delta plus of a carbonyl, making this less positive and less likely or less susceptible to attack by the hydroxide ion. So this here is preventing this reaction in a way from happening. And further, after you form this negative charge, I've forgotten to draw the arrow pushing the bond onto the oxygen here. When you form that negative charge, notice that that negative charge is pushing electron onto the system, and this methyl group is also trying to push electrons onto the system. There's a clash here. The methyl group destabilizes the negative charge in the tetrahedral intermediate. So it's very clear when we go back to here that electron donating groups slow this reaction down. This reaction is slowed down by electron donating groups that destabilize the forming anion, and electron groups will stabilize it and accelerate the reaction. And of course, if you've got that, if you've got electron donating groups slowing things down and electron withdrawing groups speeding things up, of course, you're going to have a positive slope for the reaction. So it's interesting. We've got a very large positive slope for this case where you've got negative charges coming in, a negative external negative charge coming into your reaction center, and that's accelerated by the electron withdrawing groups. So that's very interesting. So the reaction is slow with electron donating groups on the left and is fast with electron withdrawing groups on the right. That makes its slope positive. So it's interesting to note that electron donating groups destabilize the transition state of a rate determining step. And of course, just remember that our task, because the sigma values have already been set up for us, our task when we're looking at an arbitrary reaction is that we've always got to do log of our rates minus the log of the unsubstituted rate, which is the same as doing log of a rate over the unsubstituted. So laws of logs push it that way. So the positive slope is because there are electrons coming into the system. So here, if I can call this our substituent over here, I can call this our probe. We're trying to probe what's going on in this reaction center. If electrons are coming towards the probe, then of course electron withdrawing groups are going to make it go faster and the slope will be positive. So just remember that when you have a slope that is positive, when you've got a reaction constant that is positive, the system is receiving electrons. So let's have a look at a slightly different reaction. And the reaction is looking at attack of benzoyl chloride by substituted anilines. Now, note that as before, I have got my x-axis is using the sigma x values, which means that my reference shows that I'm going to plot where electron donating groups are present. I'm going to plot them on the left, and I'm going to plot with electron withdrawing groups on the right. But look where our probe is now. Over here, think about it here. What's going to accelerate this reaction? What types of R groups must you have on the system to accelerate this reaction? Electron donating or electron withdrawing? Any idea? Can you see that if you have an electron donating group over here, it's going to stabilize the formation of a positive charge at this point. So I've neglected to put a positive charge, write the positive charge over here. So just be careful that there should be a plus over here with an extra H attached. And so I'm missing out a step in that. But what happens is that if you have a electron donating group, electron donating groups are going to accelerate the loss of its electrons to attach the benzoyl chloride. Okay, so that's what we see on the graph. Can you see that the rate over here with electron donating groups is really high? However, with electron withdrawing groups, can you see that having an electron withdrawing group here is going to prevent loss of that lone pair of electrons? And so we'll have a very low rate over here. Apologies for this mechanism over here. I've missed out a step and we're missing a positive charge on the first rate of that. But please see here, this will be rate determining at this point. We'll have a pair of electrons from the nitrogen attacking the benzoyl chloride. And so as we change our R groups, we'll see that it's the electron donating that accelerates the reaction and electron withdrawing that reduced reaction. So have a look at the slope of this reaction. The slope, the reaction constant here is minus 2.69. This has a negative slope in the case where our electrons are moving away. You're losing a pair of electrons in the rate determining step of the reaction. So it's interesting that we have over here a positive slope means that a pair of electrons is coming in towards the probe where we're trying to probe what's going on with our reaction. And over here, a negative slope means we are losing a pair of electrons. We're forming a positive charge in the rate determining step of the reaction. It's really important to see the relationship between how electron donating groups, electron withdrawing groups affect a reaction and the slope, the reaction constant we get from this. So the gradient of a Hammett plot is the reaction constant. And a large positive row indicates a gain of electrons in the rate determining step. A large negative row indicates a loss of a pair of electrons in the rate determining step. So we need to just keep that in mind when we plot. So here's an example of here we have our probe and we're gaining electrons towards us. So this fragment contains our probe into the reaction where we'll place electron donating, electron withdrawing groups. And you can see we're receiving a pair of electrons in the rate determining step. And that is why our reaction constant is positive, meaning that electron withdrawing groups will accelerate this reaction. However, in this case, what we have is electron donating groups accelerate the reaction, and that's why we have a negative slope. So the question is, does the positioning of electron withdrawing groups on the left and electron donating groups on the right affect the gradient? Absolutely it does. And the convention is that we do that. And so that's why we have this table of sigma values. Those sigma values follow the convention that electron withdrawing groups on the, electron donating groups must be on the left, electron withdrawing groups must be on the right. We cannot have them the other way around because you would need to use a different set of values to switch them around. We use sigma values, the sigma x values that we get from tables, position electron donating group on the left and electron withdrawing on the right, and it forces the gradients to be this way. So please, can I ask you to remember that if you've got a positive gradient, you're receiving electrons. If you've got a negative gradient, you are losing electrons or you are donating electrons in the rate determining step. Okay. Please, if you ever have to plot the Hammett equation, and I'm going to do a quick example now where we plot it, and I will double up on that example now. Please, you've got to plot log kx over kh on the left, and you've got to plot it against sigma values on the right. So please remember, you've got to always do this kx over kh. So over here, this is an example, and it would be interesting to see. So the question is, if you have a reduction of benzaldehydes by borane, it'll be interesting to see what we can deduce from this reaction. In the rate determining step, are electrons gained or electrons lost? And I hope you can see there's some complexity with movement of electrons in places within this. So it'd be interesting to explore and see exactly how electron donating and electron withdrawing groups affect this. So have a look here. These are measured rates for these reactions. So you can see for the unsubstituted case, the rate is the rate constant is 1.15 times 10 to the 2 per second of that for this measured rate. And of course, they've done this reaction, this exact reaction with benzaldehydes with several different substituents. So they've done with the paramethoxy. Here's the rate. If you've got paramethoxy here, the reaction goes faster. If you've got the metachloro, it goes maybe a little bit slower. So let's have a look and see. Let's see if we can get a Hammett plot and see how the Hammett plot relates to this mechanism. So I've got an idea that maybe electron withdrawing groups slow the reaction down, but let's draw the plot to see what happens. The first thing I want to do, before I carry on, note that your sigma values, you don't have to read them off tables. I've read them off the tables for you over here. So the sigma values are over here. This is fantastic. This is our x-axis. These are our x values. All we have to do is now plot our y values, and then we'll get a Hammett plot. But our y values are not quite apparent here because we've got k. So I'm going to change this table around, and instead of having it in rows, I'm going to place it in columns. So here's a column. I've transcribed all of the sigma values here, over here, and I've transcribed all the rates. I've taken out the 10 to the 2s, and I've written them as a number. So the rates are in per second minus 1 over here. And you'll notice that what I've got is the rates here, and it's not quite right. It's not the relative rates that we need to do the Hammett plot. The x values are all sorted, but the y values are not right. We've got to have logs, and we've got to have relative rates for it. So the first thing I'm going to do is I'm going to have a look at the unsubstituted case. And you'll notice that the rate for the unsubstituted case is 115. So I'm going to divide everything here by 115. If I divide everything by 115, then I've got kx over kh. So kx over kh is krel. So here's kx over kh, kx over kh, kx over kh, kx over kh when x is 4cl, kx over kh when x is 3cl, and so on. So we've got to divide it from that. And of course, remember the x-axis, we've got substituent parameters, so we'll read those from the tables, and we've got to have a relative rate over here. And so when you've worked that out, you'll notice that for the unsubstituted case, the relative rate is 1, perfectly 1, which is really important, and the other values then work there. We still haven't got our y values yet. We've got to take the log of that. And when you take the log of that, we've got to take the log of that. Just please don't use ln. You must use log to base 10. You'll find that the log of 1 goes to 0, which means that for the unsubstituted, we go right through the origin. We're plotting 0, 0. That's fantastic. That's what we wanted with our graph. We wanted our graph to go with the unsubstituted h right at the middle, and then we wanted to have our other graphs on the other side. So please, this is how we build up log kx over kh. We first divide by 115 to get these values. We divide by the unsubstituted. Then we take the log of it, and we've got our y values. Now we're ready to plot the y's, our log k rels, against our x's, which we got from the table, the sigma, the Hammett substituent parameters. Okay, and so there we do it. We can plot that reaction, and when I plot that reaction, I notice that I get a straight line going through naught, and you see that the slope of that is minus 0.50. Notice that electron donating groups accelerate this reaction. Electron withdrawing groups slow the reaction down. And so this is consistent where the system loses electrons. So where we're sitting with the aromatic system, we lose electrons in the rate determining step. So if we go back here, so this here is consistent with the rate determining step. Can you see the step over here? That if our slope is negative, if this is rate determining over here, notice that electron donating groups will accelerate this and we'll have a high point over here. Electron withdrawing groups will slow this down. We have a small point over here. So our reaction constant over there, rho is minus 0.5, does show us that that is likely to be the rate determining step in this reaction. Okay. So that is a procedure of how you build up a Hammett plot, and that is how you interpret them. You interpret them based on the slope. If the slope is positive, then there's a gain of electrons towards our probe in the rate determining step. If it's negative, there's loss of electrons away from where our probe is, where we change from electron donating to electron withdrawing groups. If there's slope is negative, then we know that there's a loss of electrons, movement of electrons away, donation of electrons away from the probe in the rate determining step. Okay. Is the function of this process to find the rate determining step based on the sign of the gradient? Yes, partly. It's partly to do this, and it's partly to critically evaluate mechanisms in reactions. So if you are unsure as to the mechanism in a reaction, it's a good idea to perform the reaction with these a whole set of aromatic substituted aromatic systems for which we know the sigma values. Do your reaction for that. Measure the rates for every single substituent you can think of. Measure those rates. Do the Hammett plot, and that will help confirm the arrows you draw, whether your arrows are correct or not, in terms of finding the mechanism for reaction. And of course, that will also help in confirming the rate determining step. Okay. Right. Are there any further questions? Okay. If there are no further questions, then we will carry on with this. I'm sure by now you've got enough to go on for a couple of problems. So I'm not placing them on Are You Connected, but if you do email your solutions without marking them, I know the solutions are already available. I can mark it for you and give you feedback if you prefer me to do it rather than marking it yourself. Okay. If there are no further questions, then we'll meet tomorrow at 11 o'clock.